So after finding out a section that can withstand the given demand specified on the problem, the next thing that we have to do is to design the particular strands that will be used on this particular section that we are designing. So given this properties of 10DT34T, together with the corresponding property of the strands for 10DT34, which is a normal weight with no tapping as according to the question. We will just initially use and assume again that the strand pattern that we will use for this particular section that we have computed a while ago will be 208-D1 with uh, uh, with a distance of the pre-stressing reinforcement from the bottom fiber at the end equal to 15.5 and at the center equal to 4.25. So you have to take note that the distances that you are seeing here, the distances at the end and the center of the pre-stressing reinforcement are referred to the bottom of the section. So this means that the pre-stressing reinforcement at the end of the concrete beam that we are designing uh, is 15.5 inches from the bottom of the section at the end point. But at the center, it is 4.25. The pre-stressing reinforcement is 4.25 inches uh, above the bottom of the section that we are designing. So you just have to be careful with that. So again, the values that you are seeing here for the strand, for the specific strand pattern that we assume, are not the specific centricity of the pre-stressing reinforcement, but the distances of the pre-stressing reinforcement with respect to the bottom. So you have to be careful with that. So since we now have a section that we know will satisfy the given demands on the problem, specifically the loads, we can now design the strands that we have to use for this particular section. So again, for the design of the strands, we will use the stresses that will be induced in the concrete element at the initial pre-stressing and transfer with self-weight. So again, if you can remember, this is the pre-stressed concrete element that we are designing with a pre-stressing force P that is equal to the initial pre-stressing force PI at transfer. And then again, due to that pre-stressing force, the beam will be a simply supported beam, forcing it to support its own weight W dl, which will induce a moment at the midspan equal to MDL. So these are the internal force and moment that are acting inside the concrete element at midspan at initial pre-stressing at transfer with self-weight stage. So due to those demands or forces and moments that you are seeing here, there will be stresses that will be induced in the concrete element at midspan with a stress diagram which looks like this, with a stress at the extreme pre-compressed fiber equal to FCI and stress at the extreme pre-tension fiber equal to FTI. So again, we know that the code specifies maximum stresses that can be allowed to be experienced by the concrete element at transfer stage. So these stresses that you are seeing here, especially the extreme stresses, the FCI and FTI, must not exceed the allowable stresses that are specified on the code, especially the tensile stresses acting here. So again, obviously this is a tensile stress because it points away from the concrete element itself, while these are compressive stresses because they point towards the concrete element. So if you can remember the formula for finding out the extreme pre-compressed fiber stress, which is equal to this at transfer stage with self weight. This is actually the formula that we have derived again from the basic concept method. So we will just utilize that formula. We just express it in terms of radius of gyration and section modulus. So that is actually the actual stress that will be experienced by this concrete element at midspan at the extreme pre-compressed fiber. And again, according to the code, that stress must be less than or equal to the allowable stress specified by the code. So, uh, substituting the allowable stress specified by the code, which is actually we already computed this magnitude a while ago. So we already computed that limiting or allowable stress at transfer with respect to the tensile stress that will act on the concrete element, which is equal to 1.272 megapascal. It is just equal to the 0.25 square root of the initial compressive strength of the concrete element. So this just means that the actual stress that will be experienced by the concrete element at the extreme pre-compressed fiber must not exceed this magnitude here, 1.272 megapascal. So computing for the actual dead load for this particular concrete element that we are designing, since we already found out the section that will satisfy the minimum section modulus. So we can compute the moment due to the dead load, which is equal to 891 pound per feet. So again, we just have to compute that, convert that 891 to corresponding SI unit, which is equal to 13.01. And that dead load will produce a moment at midspan of the simply supported beam that we are designing equal to 544.615 kilonewton meter. So if we will just use the other properties of 10DT34 double T here, already specified here, and just convert them into corresponding SI, we can see that the area of this section is equal to this, and its modulus of its moment of inertia is equal to this. Uh, Distance of the extreme pre-compressed fiber with respect to the centroid or neutral axis equal to this. And using this distances specified here on the assumed strand pattern, again, the strand pattern that we are using now is just assumed. We will just check if this will satisfy the governing equations that limits the stress on the extreme pre-compressed fiber, which is a tensile stress, to 1.272 megapascal. So again, the distances specified here are just the distance of the pre-stressing reinforcement with respect to the bottom of the section. So if we will actually compute for the eccentricity, we just have to subtract the distance of the centroid to the bottom of the section to this distance that we are seeing here at center, since we are considering the midspan section. So the resulting eccentricity will be equal to this 528.828 mm. So if you will just substitute all of those terms on this equation and equate it to 1.272 megapascal, with just ensuring that you have consistent units, you can see that PI, the initial pre-stressing required so that the tensile stress that will act on the concrete element at transfer stage will not exceed the allowable is just equal or less than to this value that you are seeing here. So the initial pre-stressing force, according to the computation that we have done here, must be less than or equal to this value here, 2,818,852.27 Newton. So that must be the value of the initial pre-stressing force so that the resulting tensile stress at the concrete element at transfer stage will not exceed the allowable stress specified by the code. So given that maximum initial pre-stressing force that can be transferred to the concrete element at transfer stage, we will now have to compute how many strands will be needed, how many 1/2 inch diameter regular strands will be needed to produce that initial pre-stressing force, because we know for a fact that the initial pre-stressing force is actually the force that is being experienced by the pre-stressing reinforcement. That is just the pre-stressing force that is transferred to the concrete element. So if you can remember, you will refer to NSCPC 101-15, section 420.3.2.5. You will see this table which states the maximum tensile stress that can be experienced by the pre-stressing reinforcement at different stages during stressing and immediately after force transfer. And you can see also a similar table on ACI 318M-14, section 20.3.2.5, which is this. So that will be our guide for us to be able to find how many strands will produce the initial pre-stressing force that we have computed a while ago. So again, this is the initial pre-stressing force that we have computed a while ago. This is the maximum, actually, the maximum initial pre-stressing force that will ensure that the resulting tensile stress at the concrete element at transfer stage will not exceed the allowable stress specified by the code. So in order to produce this magnitude of initial pre-stressing force, the number of strands, the force that will be coming from the strands must be equal to this formula that you are seeing here. Given that the maximum stress that will be experienced by the pre-stressing reinforcement transfer is just 0.7 FPU according to this table that you are seeing here immediately after force transfer. So you can see here that the code specifies a maximum of 0.7 FPU tensile stress that will be experienced by the pre-stressing reinforcement immediately after force transfer, which is the stage that we are talking about here. And given that maximum stress, tensile stress that can be experienced by the pre-stressing reinforcement, if we want to change that or convert that to its corresponding force, we just have to multiply it to the corresponding cross-sectional area of the pre-stressing reinforcement. So if APS is the cross-sectional area of one strand and N is the number of strands, therefore the total force that will be acting on the pre-stressing reinforcement will just be equal to the product of these terms that you are seeing here. And then with just substituting the corresponding values that you are seeing here, FPU is already given on the question. APS is the area of a 1/2 inch diameter standard strand as specified on the property of a 10D T34 section. Therefore, we can just compute for the magnitude of N after substituting the corresponding values of FPU and APS. So again, FPU is specified on the problem equal to 1826 megapascal, and the area of a 1/2 inch diameter regular strand is equal to 99 mm squared. So you have to be familiar with the area of a 1/2 inch diameter regular strand. So the only unknown on this equation is the N, the number of pre-stressing strands that will produce a maximum magnitude of initial pre-stressing force equal to this. And computing this equation, we can see that uh, a maximum number of strands equal to 22 strands or 22.28 strands to be specific will produce that maximum initial pre-stressing force. But then again, since we want our initial pre-stressing force to be equal or less than, take note, less than this magnitude here, we can just round down this n that we have computed here so that we will be assured that the resulting pre-stress force that will act on the pre-stressing reinforcement will not exceed this maximum initial pre-stress that we have computed. And with that, we will be assured that the tensile stress that will act here, the maximum tensile stress that will act here on the concrete element at transfer stage will not exceed the allowable stress specified by the code. So therefore, Since the requirement is 22 strands, and we have assumed that the strand pattern that we have used is 208-D1, uh, we can say that the strand that we have assumed is okay, because may I just remind you the meaning of the strand pattern. The first two digits here stands for the number of strands for this particular strand pattern. So 20 means there are 20 strands in this particular strand pattern. The third digit here is actually the diameter of the strand uh, with respect to 16 of an inches. So meaning the diameter of the strand that is used here on this particular strand pattern is 8 over 16 inches, or simply 1/2 inch diameter, as already specified on the properties of 10DT34. And then the D here is actually stands for depress, or depression, number of depression. So we have used the dash D1 strand pattern instead of the dash S. The dash S strand pattern, if you will try to look back on the previous slides, the dash S strand pattern pertains to strand patterns that has straight tendons. S stands for straight tendons, meaning the tendons or that particular strand pattern has a constant tendon eccentricity, which is not the case obviously on this particular problem, because we have a harp tendon which has a variable tendon eccentricity. So we can just choose between the strand patterns which has dash D, which has a depress tendons. So since we have assumed that 28-D1 is the strand pattern for the section that we have computed or derived a while ago, and that since we have seen that the maximum strands that we need to produce this maximum initial pre-stressing force is just equal to 22 strands, which is obviously greater than the actual strand on this particular strand pattern. Therefore, this strand pattern will obviously satisfy the requirement that the resulting initial pre-stress must be less than or equal to this value that we have computed here. Because obviously if you will substitute 20 here in place of n here, obviously the resulting initial pre-stressing force will be obviously less than this, which is our goal. So why is that? Why do we have that goal? It is simply because uh, if we will have a larger magnitude of initial pre-stressing force, the 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 tendency is there will be a larger tensile stress that will be produced on this particular extreme pre-compressed fiber, which will therefore eventually exceed the maximum allowable stress specified by the code. So we don't want that to happen. We want our design to be code compliant always. That's why we might as well just use a strand pattern. Actually, this is the maximum number of strands that is available for a 10DT34 double T. So might as well, uh, we just have to use a strand that has a number of strands that is equal or less than to this number of strands that we have computed here. And obviously 20 strands is obviously less than 22 strands. Therefore, the strand pattern that we have assumed initially is okay. So therefore, we can use 20 1/2 inch diameter strands, or 28-D1 strand pattern. So with that, since we have already computed the particular strand pattern that we will use on this particular problem, we can now compute for the actual initial pre-stressing force that will be induced by this 20 1/2 inch diameter strands. So again, how can we compute for the actual PI? We can just again use this equation. So we just have to change the magnitude of n, which will be now equal to 20. So therefore, the actual initial pre-stressing force that will act on this particular section that we are designing will now be equal to 2,530,836 Newton. And if you can recall, we have derived a while ago that the ratio of the effective pre-stressing force and the initial pre-stressing force is just equal to 0.82. Therefore, if we will compute for the initial, if we will compute for the effective pre-stressing force, we just have to multiply 0.82 by pi, which is this. So therefore, the actual effective pre-stressing force will be equal to 2,075,285.52 Newton. So these are the values. These are the actual pre-stressing forces that will act on the pre-stressing reinforcement that we are designing here. And again, we have chosen this to ensure that the tensile stresses, or the maximum tensile stress that will be induced on the concrete element that we are designing at transfer stage will not exceed the allowable stress specified by the code, which is 1.2 megapascal, if you can remember from the previous slides. So after that, actually the design process already ends. The design process already ends on that part, although we still have to check the adequacy of the design that we have made. So how can we check the adequacy of the design that we have made? So we just have to make sure that the corresponding stresses that will be induced by our design section at different stages of pre-stressing will not exceed the allowable stresses specified by the code. So meaning we have to check the stresses that will act on the pre-stressed concrete that we are designing on transfer stage as well as on service load condition. Although for the case of the stresses acting at midspan, actually we already checked its adequacy at transfer stage. Actually, that is our basis a while ago from the previous slides. The stresses acting at transfer stage at midspan is the basis on the design of the strands or the pre-stressing reinforcement that we will use on this particular section that we are designing. So therefore, automatically we can be assured that our design is adequate, is conforming to the allowable stresses specified by the code at transfer stage. So therefore, we just have to check its adequacy at service load condition, wherein uh, the loads that are acting on the concrete element are now due to the dead load, superimposed dead load, and live load. So this is our design, the design that we have computed a while ago. We have seen that 10DT34 with strand pattern 208-D1 is sufficient enough to resist the given demands on the problem. Although again, we just have to check its adequacy at different stages of pre-stressing. So again, the resulting stresses at the concrete element at different stages of pre-stressing must not exceed the allowable stresses specified by the code. So since this is the design that we have designed a while ago, and these are the properties of the section, so you can refer here on PCI 2010 for the particular properties of 10DT34, as well as the property of a 28-D1 strand pattern for a normal weight no tapping concrete. We can now check the adequacy of this particular section that we have designed with respect to the service load condition. So again, at service load condition, additional stresses will be induced due to the application of the superimposed dead loads and live loads, which has now, at service load condition, the pre-stressing force that acts now on the pre-stressing reinforcement is the effective pre-stressing force, and the moment is now due to the dead load, live load, and superimposed dead load acting at midspan. So we just have to check the the resulting stresses that will act on this concrete element at service load condition. And again, they must not exceed the allowable stresses specified by the code at service load condition. So the resulting stresses here is obviously something like this, with a extreme pre-compressed fiber stress equal to this, and extreme pretension fiber equal to this. So again, if you can take note here, I have used a small letter F to indicate that the stresses that we will now computing here are the actual stresses. So again, if the letter is capital, it specifies an allowable stress, but uh, if it is a small letter, it signifies actual stresses. So if you can remember the formula for finding out the stress at the extreme pre-compressed fiber from the basic concept method that we have derived or we have discussed from the previous meetings, the formula is equal to this. That actual stress acting at the extreme pre-compressed fiber again must not exceed the stress specified by the code, which is this. We already computed this a while ago. The maximum or the allowable stress allowed by the code at service load condition with respect to the maximum compressive stress that will be experienced by the concrete element. So with just substituting the corresponding needed values or terms here, which are the effective pre-stress force that we already computed a while ago, which is equal to this, and then the area of the concrete element that we are designing, you can get that properties, or you can get those properties here on PCI 2010. You can see that the area of this concrete that we have chosen, 10DT34, it has an area equal to 855, or if we will convert it in SI, it is equal to this, as well as the moment of inertia, the distance of the centroid to the extreme pre-compressed fiber, or simply the top fiber, and the eccentricity of the pre-stressing reinforcement EC at the midspan, which is equal to this. So we already computed all of those a while ago. And then, additional to that, we need to know the moment due to the dead load, which will be coming from the weight of 10DT34, which we already computed a while ago as well, and as well as the moment due to the combined superimposed dead loads and live loads. So we already computed all of this a while ago. So all we have to do is substitute them on this equation and make sure that the resulting stress will not exceed this magnitude of maximum compressive stress that can be experienced by the concrete element at service load conditions specified by the code. So if you will substitute all of those terms here, you can see that the resulting actual stress at the extreme pre-compressed fiber will be equal to this, which is actually a compressive stress, because obviously you will compute for a negative stress here, which signifies that the stress is actually a compressive stress, which is obvious on this stress diagram. So again, if you will compare that to the allowable, obviously that is less than the allowable compressive stress specified by the code that can be experienced by the concrete element at service load condition. Therefore, our design is okay with respect to the maximum compressive stress at service load condition. But for the case of the maximum tensile stress, we just have to again compute the actual tensile stress, which is this, acting on the concrete element at service load condition, which will be equal to this. Again, this formula just came from the formula that we have derived from the basic concept method. We just express it in terms of radius of gyration and section modulus. So now we need to use the distance of the centroid to the extreme pretension fiber, or simply the bottom fiber, which is equal to this, which came from the property of the section that we are checking, the 10DT34. So again, according to the code, we already computed this a while ago. The tensile stress, the maximum tensile stress that can be experienced by the concrete element at service load condition must not exceed this stress here. This is specified on the code. So substituting all of the required values here, you can see that the stress acting on the bottom fiber of the concrete element that we are designing is equal to 0.279 megapascal, which is actually a compressive stress. You can see that the stress that you will compute here has a negative sign, meaning it is not actually a tensile stress like what we expected here, but actually a compressive stress, which is good. That is better actually. Why? Because we don't actually want our concrete element to experience as much as possible tensile stresses. And with this actual stress that we have computed here, we have seen that the actual stresses that will be experienced by our concrete element, given the demands on the problem, will uh, will actually not tensile stresses at the bottom fiber, but actually a compressive stress or stresses, which is actually good. So that is actually good for our design. So again, instead of comparing that to the maximum tensile stress that is permitted to be experienced by our concrete element at service load condition, we have to compare that to the maximum compressive stress, because obviously it is a compressive stress. So we have to compare it to the maximum compressive stress that can be experienced by the concrete element at service load condition specified by the code. And obviously, this is very less than the allowable. Therefore, the section that we have chosen is okay with respect to service load condition at midspan, at the critical section. But additional checking is required for the end supports actually. So we need to also check the adequacy of the section that we have chosen with respect to the stresses acting at the end supports. So it's not enough to check the adequacy of the section with respect to the midspan or the critical section. You also need to check the adequacy of the section that we have chosen at the end support. So we have to make sure that the resulting stresses that will be induced at the end supports will not exceed the allowable stresses specified by the code. So again, starting the checking at the end supports of the section that we have chosen, which is 10DT34 with strand pattern to 8-D1, which has this corresponding properties here and properties here that can be found on PCI 2010. So starting the checking on the stresses that will be induced at the end supports at transfer stage with self-weight, wherein the pre-stressing force acting on the pre-stressing reinforcement is just equal to initial pre-stressing force, and the bending moments that will act on the end supports will be equal to zero. Obviously, again, because our beam is just simply supported. Therefore, there will be no moments at the supports or end supports. So the resulting total stress acting at the end supports at transfer stage with self-weight will be like this stress diagram, with a extreme pre-compressed fiber stress equal to this and extreme pre-tension fiber stress equal to this. Again, small letter has been used, therefore the stresses that you are seeing here are actually actual stresses. These are actually the actual stresses that will be experienced by the end supports at transfer stage with self-weight. So if you can remember the formula for finding out the stresses acting on the extreme pre-compressed fiber at transfer stage coming from the basic concept method, you will have this formula here. So we just disregarded the flexural stress due to the bending moment because obviously there is no bending moment at end supports. So we need PIAC, EEC, ECC, and R squared, or simply the moment of inertia, for us to be able to find or compute this actual stress acting at the extreme pre-compressed fiber. And according to the code, you have to remember, according to the code, that actual stress that will be experienced by the concrete at the extreme pre-compressed fiber, which is actually a tensile stress, according to this diagram, because this stress here points away from the concrete itself. Obviously, it's meaning it's a tensile stress that, and similar manner, these stresses that you are seeing here that point towards the concrete itself are compressive stresses. According to the code, the tensile stresses that can be experienced by the concrete element at transfer stage must not exceed 1.272 megapascal. So the actual stresses that we will compute here must not exceed this allowable stress specified by the code. So if you want to compute the actual stress, we need PI, the E, the CC, and ACR squared, or simply the moment of inertia, which are actually already computed a while ago. So the actual PI, if you can remember, is just equal to this, and then the area of the section, we already converted it to SI, as well as the moment of inertia, and the distance of the centroid to the top fiber, and the distance of the centroid to the bottom fiber. And this is actually the eccentricity at the end supports. Again, you have to be cautious. The eccentricity that you will use now for the checking of the adequacy at end supports must not be the 4.25 but the 15.50 uh, distance of the pre-stressing reinforcement from with respect to the bottom of the section at the end. So you have to use the values specifically for the end of the section or beam that we are designing. So again, the value that you are seeing here is the distance of the pre-stressing reinforcement at the end of the concrete element that we are designing with respect to the bottom. So if you want to find the actual eccentricity at the end of the member that we are designing, we just have to subtract this to the distance of the centroid to the bottom fiber or bottom fiber of the section. So you can compute that eccentricity is equal to this. So again, with just substituting all of the corresponding values here, you can see that the actual stress that will be experienced by the extreme pre-compressed fiber, which is supposedly a tensile stress, but we computed it as a compressive stress equal to 0.438 megapascal. So the actual stress acting at the extreme pre-compressed fiber, which is supposedly a tensile stress, is actually a compressive stress, which is again a good stress because again we want our concrete to experience, or I mean, we don't want our concrete to experience as much as possible tensile stresses because we know that our concrete has a very low strength to resist tensile stresses. So this compressive stress here that you are seeing here is actually okay. So instead of comparing it to the maximum tensile stress specified by the code, we have to compare it to the maximum compressive stress specified by the code that can be experienced by the concrete at transfer stage. So therefore, since it is less than the allowable, therefore it is okay. So next is the stresses acting at the extreme pretension fiber. So again, the formula is similar to this. We just have to change the sign from negative to positive and the corresponding C. So we'll now have to use the C with respect to the extreme pretension fiber. And again, according to the code, that actual stress that will act on the extreme pretension fiber must not exceed this maximum compressive stress because obviously, according to the stress diagram, we are expecting that the stress acting on the extreme pretension fiber is actually a compressive stress because it points towards the concrete. So again, after substituting the corresponding values for this formula, you can see that the actual stress that will act at the extreme pretension fiber of the concrete element at the edge supports at transfer stage will be equal to this. So it is negative, obviously. So our expectation is was met. Our expectation was met. We are expecting a compressive stress and we have computed a negative stress. Therefore, it is a compressive stress. But the problem now here is if we will compare it to the allowable or maximum stress, compressive stress that is specified by the code that can be allowed to be experienced by the concrete element at transfer stage, you can see that the actual stress is greater than the allowable stress. So, what could be the solution for that? How can we correct the design at the end supports at transfer stage so that the resulting stress at the bottom fiber will not exceed the allowable stress specified by the code? So the solution for that is we can change the magnitude of the eccentricity of the pre-stressing reinforcement. So we will now just have to compute what must be the magnitude of the eccentricity at the ends of a simply supported beam so that the resulting stress at the extreme pretension fiber will not exceed the allowable stress specified by the code. So how can we compute that? How can we compute that that eccentricity? All we have to do is uh, substitute the maximum stress allowed by the code in place of the FTI here. So again, just take note that the code specifies this as the maximum allowable compressive stress. So we have to indicate its direction here, which is again must be negative to signify that it is a compressive stress. And then just equate that here to the formula that we have here. We just need to change the magnitude of E. So the E that we will be computing here will be now the actual eccentricity at the end supports. So if we will again substitute the corresponding values of PI, CT, and the ACR squared, or simply the moment of inertia, the corresponding value of E that we will compute is equal to this. So meaning the eccentricity at the ends of this simply supported beam that we are designing must be equal to this, so that the stress that will be produced at the extreme pretension fiber, which is a compressive stress, will not exceed the allowable compressive stress specified by the code at transfer stage. So if you will want to check, you can just substitute this in this particular formula here to find the actual stress that will act on the extreme pretension fiber. And you can see that that particular stress will now be less than the allowable stress specified by the code. So therefore, we must change the magnitude of the eccentricity at the end supports in order for our design to be code compliant, in order for our design to not produce stresses that will exceed the allowable stresses specified by the code, specifically at transfer stage. So that is just the checking of the adequacy of the design with respect to the transfer stage. So we just have to check it once more for its compliance to the code on the service load condition, wherein additional loads will be applied to the concrete element that we are designing. And the pre-stressing force that is acting on the pre-stressing reinforcement at this particular stage of pre-stressing is already the effective pre-stressing force. So with that, the resulting stress diagram at the end supports will look something like this, with a magnitude of the stress acting on the extreme pre-compressed fiber equal to this, and for the extreme pre-tension fiber equal to this. So again, at this service load condition, the magnitude of the pre-stressing force acting at the pre-stressing reinforcement is already the effective pre-stressing force. But the bending moment acting on the ends of the simply supported beam that we're designing will still be obviously equal to 0, because there is no moment at the end supports of a simply supported beam. So again, using this similar formulas as what we have discussed on the basic concept method before, which is this, we can now compute for the actual stress acting at the extreme pre-compressed fiber FCS at service load condition. So again, according to the code, that actual stress, which is actually a compressive stress, must not exceed uh, 15.525 megapascal. So again, we just have to substitute the corresponding terms here in order for us to find the actual stress that will be acting at the extreme pre-compressed fiber at the end supports at service load condition. And again, that actual stress must not exceed the allowable stress specified by the code, which is this, which is a compressive stress. So again, we just have to substitute all of the corresponding terms, which are the effective pre-stressing force, which we already computed a while ago, which is equal to this, and then the corresponding actual eccentricity at the end. So take note, we already changed the magnitude of the eccentricity at the end supports in order for our design to be adequate with respect to the transfer stage. And the actual eccentricity we have computed a while ago is equal to this. So that is the eccentricity now that we will be using for checking the adequacy of our design with respect to the service load condition. So if you will substitute all of those on this formula, you can see that the actual stress that will act on the extreme pre-compressed fiber at service load condition is actually obviously a compressive stress as expected according to this stress diagram here. which is obviously less than the allowable compressive stress that can be experienced by the concrete element at service load condition. Therefore, the design is okay with respect to that checking. But again, the last checking that we need to know is the compliance of the stress acting on the extreme pre-tension fiber with the allowable tensile stress specified by the code. So you can see here, we are expecting that the stresses acting on this part of the concrete element is actually tensile stress. So the formula for finding the actual stress here at the extreme pretension fiber is equal to this, similar to this formula. Just have to change this to positive. And again, according to the code, that actual stress acting here, which is actually a tensile stress, must not exceed the maximum tensile stress specified by the code that can be experienced by our concrete element that we are designing at service load condition. So that actual stress must be less than this allowable stress here. So again, substituting the corresponding values needed, you can see that uh, the stress acting on the extreme pretension fiber that is expected to be a tensile stress is actually a compressive stress, which is again a good value, because again, as much as possible, we want our concrete element to not experience tensile stresses. So as we have computed here, we have seen that the actual stresses that will be produced at the bottom fiber of the section that we are checking is actually a compressive stress instead of a tensile stress, which is again a good value. So if we will compare it to the allowable compressive stress specified by the code, which is this, we can see that it is less than the allowable, therefore it is okay. So since all of the checking that we have done satisfied the already satisfied the demand given by the problem, as well as the maximum permissible stresses specified by the code. Therefore, we can say that the section that we have chosen is adequate to resist the given demand by the problem, as well as uh, the resulting stresses and the simply supported beam that we are designing will be assured to comply with the maximum permissible stresses specified by the code. So therefore, we can use a section 10DT34 with a strand pattern 208-D1 with mid-span eccentricity equal to this, which can be found on the property of the 208-D1 strand pattern from the PCI 2010 design handbook, and an eccentricity equal to this, which is actually the actual eccentricity that we have computed, that is required to be the eccentricity at the end supports of the simply supported beam that we are designing in order to produce stresses that will not exceed the allowable stresses as specified by the code. So the properties of that section and strand pattern can be found again from PCI 2010. So these are the properties of the section that we have chosen that can withstand the given demand specified by the problem. So that is the final answer on this design problem.